Oh my.先两个一起冲。
你这样划掉了。
没有没有，这个放这儿，没冲。
有多贪心。这个是原价哎。
嗯。
我当时买的时候好像不是原价的。
你不100多吗？
对，但我那打。
你买的上面那个，上面色球上那个。还是这个？
我买不是这个，不是这个，不是这个，这个是这种充电器。
买这个。
也没有它这个这么贵。我买的不是9700无影响力，但我忘了是。我们不是在 Best Buy 上买的吗？可以查一下。
这不是 Best Buy。
History。
好的吗？好吧。
3是你的，那你的照吗？不是这个。
感觉可能是你的账户。
点了。
点了。
我买了怎么弄？是这样。
那我就买。
不行。
为啥呀？
只有这一个吗？不可能啊！那个呢？
你在另外账户。
原价买太亏了，东西打折了都。
Hello, everyone. Welcome back to our data mining course on this lovely Wednesday night. All right, so today we are going to continue looking at MapReduce, and let me share with you the slides. All right, so still remember what we have been talking about last time? Yes? No? So we covered, what have we covered? We covered cluster environment. All right, let me just quickly recap. All right, so you should be able to see the whiteboard. So last time we were talking about if you have a really large data set and you only have a single computer, single node architecture, it will take a lot of time to process them, right? CPU, memory, and disk. Right, so your data is on the disk, you have to read into memory, processing the CPU, and coming back to the disk. Because the data could be, let's say, 20 terabyte, but your memory is only 64 gigabyte. Right, so every time you need to read 64 gigabyte, processing the storing the memory, processing the CPU, save the result back to the disk, and read the second batch. And we look at that Google example. Say if you want to process the entire web, it will take you, if I remember correctly, 46 days. So what would be a good solution? Let's just buy a large number of all these computers and connect them together, right? So we look at things like a cluster. You have different, well, you will have multiple racks. Each rack, you will have multiple computers, and they will be connected by a switch and more switches and all that. Now, instead of having one computer to process the entire file, you have multiple computers, so you will be able to process them in parallel. And this is the hardware part. But what about the software? How do you write a program to be able to process all this large data set in parallel? So we talk about the challenges in working on large data set in a cluster environment. And we say MapReduce can help us to solve this problem. So the first distributed file system, H is Hadoop. The first component that we look at is this distributed file system, right? So if you want to be able to parallel process the large data set, you will need to be able to read all your data sets in parallel. So you might have multiple computers and you have a large file. You first slice your large file into small chunks. And for each chunk, you will store it on multiple machines. Right, so this is machine, 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 and machine. And they can be on the same rack, can be on different racks. And now if we want to do parallel processing, we'll say, hey, machine number 1, you just process this one. because you store this data set, right? And machine number 2, you just process this one because you stored this one. Okay. So this is the distributed file system. And one nice thing about this distributed file system is the same chunk. It's stored in multiple places so that if one machine died, you will still be able to recover them from other machines. So this is nice. But how about writing a program to access the data and coordinate all the computation? That's how our MapReduce framework comes in. And we talk about MapReduce. It's not a programming language, it's a programming model. I know that the concept of a programming model might be very abstract to you right now, but just think about the implementation would be Spark. So this means you will be able to write MapReduce programs code in a way that will be able to enable the process of large data set. And in a large MapReduce framework, we look at map function, reduce function, and shuffling. And we say that shuffle is handled by the implementation of your MapReduce environment, but you have to write your map function and reduce function. That's it. That's MapReduce. This framework or this programming model is extremely flexible, so you will be able to write your code to process many different things or to do many different things. And today we're going to look at some of the examples of MapReduce code, but always think about input, process, and output when we are going through our examples today. All right, so let's look at the slides. So we look at reading a document and counting unique words from the document, right? So I think it's somewhere here. This one, right? So just a recap, this is a large document and our goal is to be able to count the occurrence of each unique word. So for example, we want to know, all right, crew, the word crew appears twice in the document. And the problem is the document is too large. We will not be able to use one single machine to process it. So in this case, we have sliced the document into 4 parts and process it by 4 computers. So this computer, this map function works on this part. The second map function works on this part, and the third and the fourth. Once they all process their corresponding chunk, the group by key, the shuffling process provided by Spark or your MapReduce implementation will sort the output of the map function and then notify the reduce function to take all the sorted one and aggregate the value, right? So if you look at here, there's 2 crews, could be from two different map functions, and the reduce function will just say, all right, I have 1 record, I have 2 records, and I will just add their value. This means we only see crew twice in the entire file. So very simple example of MapReduce. Okay, so more formally, let's look at the definition of MapReduce. The input is always a set of key value pairs. So if you're not familiar with key value pairs, just think about it something like this. With a comma in between, you have an object here and another object here, okay? So I say object because it's very flexible. You can store an integer, you can store a string word, you can also store a set, word, and so on, okay? And for the value, it's also very flexible. You can store anything that you like. And we are going to see some examples. For your map function, the input is key value pairs and the output is also key value pairs. Okay, so they are not the same key value pairs. It's always key value pairs. So it takes a key value pairs, output a set of key value pairs. For example, your key, the input, your key can be a file name. Your value will be a single line in the file. And there is one map call for each key value pair. So this might be too abstract for you, but we are going to look at some examples so it becomes clear. In the reduce function, you do the same, but it's very interesting if you look at here, you still have the key, but now your value is a set, right? So now this is before in the map function, the output is one value, but now you have a set of values. And the goal for a reducer or a reduce function is to take all the key value pairs with the same key, aggregate this value set, or do some process of the value set and generate a new value. So this is generally what we are looking at for a map reduce function. Let's look at one example. The same example we did before, word count. In your map function, the input would be the document name so that your map function knows where to find the documents. The value would be the text of the document. One thing that's also very important that you will see in all this example, it's you always have to have two things here, but sometimes you can have dummy values. Just hold that thought, and I will tell you what does it mean for dummy values. If you look at the implementation of the function, it says for each word W in the value, right? So the text in the document for each word, I will just produce or I will just output this word and a value 1. Okay, so this means the function see this word once. For a reducer, the key will still be the input, key will still be the word, and the value will be an iterator over the counts. So for example, start by result equal to 0. For every count in the values, I'll just add them up, right? And eventually you will sum up all the values and produce the key and results. So let me give you one example. Let me see if I can annotate it. So there's a question, is shuffling done on the map nodes? No, shuffling is done on the other nodes. It's the primary node that is coordinating all this computation. We are going to cover that in the second part of MapReduce. That's a very important thing also. All right, so if you look at this, let me just give you one example. An example input for the map function, it could be file name, could be, let's say, web.html. HTML. And the value will be all the strings, the characters in the web. For example, we will have hello, world, home page. Okay. And in the map function, for each word in this value, right? So for each word, that means we're going to iterate through this text. The first word will be hello. So it will produce hello and 1, right? So this is a key value pair. Then it will produce world 1 and so on. Okay. Let's add one more word. Say hello world homepage and hello. Okay, assuming this is the web page. So eventually it will also produce another hello and 1. In the reducer, your reducer, after the shuffling steps, your reducer will receive some of this as the input, depends on which reducer it got assigned to. Say you have 2 reducers, R1 and R2. Okay, they're all running the MapReduce program. So your first reducer gets all the keys hello. So it will say, all right, I have hello. The shuffling function will give me this 1 and 1. So why do I have 2 1s here? Anybody?
Because there are 2 hello 1 pairs.
Right, exactly. Because it has 2 hello ones. And it's grouped by key. And think about this. Now I'm looking at one map node, right? So this is the map function from one map node, but you could have more than one map node. So this value can be much larger, can be longer than just 2, because we only have 2 from here. So in this case, your reduced function, look at the count and look at the key. It will say, all right, so I'll just take 1 and 1 as 1 plus 1 equal to 2. And that will be the number of occurrence of hello. Okay, so it's really nice about this is because the same reduce function, the same map function can run on multiple machines. You don't have to write them separately. You don't have to do the coordination because the shuffling steps already help you to handle that. The only thing that we have not covered is how the data flow from one machine to another, and we're going to do that next. All right. So let's look at some examples. Input is key value pairs. So you have some key, you have some value. Intermediate key value pairs is in the map step. You are going to generate some key value. In our example, the word count. This is the word. This is 1. Right? And the shuffling step by the MapReduce environment, your Spark, will take all the intermediate key value pairs from every map node. Remember, we will be running this on a large cluster, so this could be result from 1,000 machines. And the primary node will look at this 1,000 machines output and shuffle them and tell the reducer which one you need to get. So this is after shuffling, they got grouped together by key. The reducer will take this as the input and generate something like this. So it's interesting to look at this chart because if the shape is the same, it means it doesn't change data type or values. You can see that this is one value here and you have multiple values after shuffling. But after the reducer, the value type got changed because this could be a summation of all the values before, right? So other nodes as well. Okay, so let's look at other examples. So one example of using MapReduce, a common way that you want to use MapReduce is to build an inverted index. So what exactly is an inverted index? Well, if you look at the input here, you have multiple tweets. And we want to build an inverted index. So if someone queries breakfast, we want to say, okay, I will return tweet 1 and which one? Tweet 3, right? Because 3 also have breakfast. If someone query pancake, what would be the tweets that you want to return? Anybody? 1 and 2. Right, so 1 and 2 has pancakes. Great. So that's our goal. And if you look at our desired output, this is exactly what we want to do, right? So if someone query for pancake, we want to return tweet 1 and tweet 2. Breakfast, we want to return this. Okay, awesome. Assume that you have a really large file, store all the tweets, 20 terabyte. How do you write a MapReduce program to distribute this task, this generating inverted index task into 1,000 machines? What would be your map task and what would be your reduce task? So I'm going to show you what would be a good way to think about how you write this function. So you always from the output. You look at the input, you decide your desired output, then you can decide the key that you want to use in the reducer, right? So ideally, in your reducer, you want to have something, key value pairs with key like pancakes, because your output looks like that. So if this is what you want, what would be the key value pairs for your map task? Well, for your map task, this is your input. You have key, tweet 1, value, the content of the tweet. For each word in the input value here, you want to produce something like this, right? You want to say, okay, I is a word. It's in tweet 1. Okay, what will be your next key value pairs that you will produce? You have love and also tweet 1, right? Love will be your key, tweet 1 will be your value. And what would be your reduce function then? What would be the input for your reduce function? Well, from this example, you might be able to imagine your input for your reducer or reduce function is something like this: pancake. And what would be the value? Okay, great. Yes, list of tweet IDs, right? T1 and T2. And what would be your reduce function then? Yes, so your reduce function will just produce that output, take the input and just output it, and you're done. So what do we learn here? Sometimes your map task or your reduce task doesn't have to do anything. But you still have to have it because you want to maintain this outline of your map reduce program, okay? Any questions before we move on? All right, so second example, we're going to look at multiple examples. So bear with me. In a social network, we want to find how many friends does each person have. So look at your input. This is key value pairs. This tells you that Jim and Sue are friends. So Jim is the key, Sue is the value, right? So it can be that you parsed some file or some social network website, and this is what you find, what you found. And your desired output will be Jim and 3. Then what would be your key in your map task and your reduce task? Because ideally, we probably want to look at this and start to parse out how many friends Jim and Sue and other people has. And in the reducer, we want to aggregate all the result, right? So think about your input here. This can be a very large file. We need to slice them into 3 parts. So met function 1 works on here, 2 works on here, and 3 works on here. right? So we can do this in parallel because M1, M2, and 3 will work on parallel, and your reducer will be in charge of merging them. So great, name of the person and 1. So let's look at it. In your map function, you will take all this input and output something like this. What does this mean? It says, all right, I know that Jim has a friend, 1. So Jim has a friend. Sue also has a friend, so Sue 1. Lin has a friend, Lin 1, and so on. Just remember all the example here, all the examples that we are showing here. This is just one way that you can write the MapReduce functions. If there's many ways that you can do this. So what would happen after shuffling? After shuffling, every records, every key value records that has Jim as the key got organized into 1 records, and this becomes the input of your reduce function, right? So what would your reduce function do? Well, we would just look at this 1, 1, 1, and then put them together as 3. That's it. So very easy. Let's look at another example. We want to write a MapReduce algorithm, take a very large file of integers, produce as output all unique integers from the original file that are evenly divisible by 7. Great. That means we are looking for 7, 14, 21, and so on. You cannot feed a large file into the memory of a node, so we want to do MapReduce. What would be your map task? Each map task will get a chunk of the file of integers and process it, right? So we already know this. In your map function, for the integer list, we will just produce v and 1, which means map function tells you what? I saw this integer once, okay? In your reduce function, it will eliminate duplicates because let's say if you map function says 3 and 1, this means map function is telling you that it saw the number 3 once, right? But it can see this number, it could see this number 3 multiple times. So eventually your reducer might have some input looks like this. 1, 1, 1. But because we only care about if an integer is divisible by 7, we don't really care about how many occurrence. We don't care about the occurrence of 3 here. So we just ignore the duplicates, ignore all the value here. We just take the value and we just divide it by 0. And we say if it's divided by 0, well, sorry, divided by 7 equal to 0, we will just produce this. This should be key, not V. Right? Because in this case, you are taking 3 mod 7 to see if you have a 0. If you do, you produce 3 and 1. And well, 3 is not going to be evenly divisible by 7. So let's use 7 as an example. Okay, so this could be an input for your reducer. And you take 7 mod 7 equal to 0. You will just produce 7 and 1. So question for everybody. In this case, when your reducer produces 7 and 1, what does that 1 mean?
That it is divisible by 7? Like a binary?
Well, that 1 doesn't really mean anything. It's a dummy value or a placeholder because you always have to output key value pairs. This doesn't really mean anything. Only this key is important. You can also, if you want, you can produce 1 and key. This just means here in the result, the key is a dummy value, but the value is actually the result we want, right? So your next program needs to know how to read the result. So there's a question, the key doesn't have to stay the same. No, you can generate whatever output you like. Sometimes you are going to write multiple map reduce functions. So the reduce result will be the output, the input for the next map function. You just need to be able to write the code to coordinate them. Okay, so there is also one interesting thing here. So instead of checking if the value would be able to evenly divisible by 7, can we do it in the map function? Well, we can, right? So before we send it, before the map task send it to the reducer or send the result to the shuffling function, we can already check. We can say if the number is evenly divisible by 7, given this condition here, we will produce a key value pair. If it's not, we are not going to produce a key value pair. So one thing that's very interesting to think about is what's the difference if we between putting this condition in the map function and putting the condition in the reducer. Because you always have to check, right? This one computational step, do we gain anything? Okay, so people are answering it. Duplicate values would add to processing. Yes, but this is actually not that important. Save more memory, it doesn't really save much. Less communication cost. Okay, yes. It's very, very important to know that now you are saving communication cost. So one thing that's very important in writing MapReduce function is you want to eliminate or you want to minimize the data you want to transfer across machines. Remember, we look at the rack, we look at switches, connecting racks, connecting machines on a rack. The slowest, when you have large data set, suddenly many things doesn't make sense. So for example, we were working with a company to process large satellite imagery, okay? So that's multiple terabyte. Instead of giving us a web link or FTP site to download the data, they just store the data on a hard drive and just fade access the data. That's actually much easier than us downloading data from their website. Because transferring large data set on the internet is very slow. Transferring data set across machines is very slow compared to transfer data within one single machine. So think about reading files from your hard drive well, think about this. If you have 2 computers, you want to read 10 photos on your local computer. It will be much faster compared to reading the 10 photos from another computer on the same network, right? So you want to reduce the communication cost. And remember, in MapReduce, you always assume your map function and your reduce function are running on different machines. They don't even have to be on the same rack. So if you can eliminate the number of key value pairs you want to produce and consumed by the reduce function, you will be saving a lot of communication cost and the runtime for the entire program, okay? So the next example, we want to find the largest integer in a very large file. How do we do it? Each map task will get a chunk of the file of integer. So we're going to parallel process this, right? So think about, you have a large file, you have let's say you have 4 people. 4 people wants to find the largest integer. So you're going to divide the files into 4 parts, give each person a portion of the large file. And what would this person or the map task produce? Well, it will produce something like this. So say if you have 3 map tasks or machines that are running this task, the first machine takes this as input, second take this as input, third take this as input. It's worth noting that this is not a key value pair. It should be written as a key value pair, right? This is the value. And the key could be the file name, could be a dummy value, because your map function doesn't really need the key. Even if the file name is here as the key, your map function is not going to use it, right? It will just read all these values and say, okay, in this list of integers, the largest number is 10. And I will use 1 as the key, 10 as the output. What would be your reduce function? Well, after your shuffling and group by key, you will only have 1 key value pair because every map function uses the same key. This indicates what? You have only 1 machine. Well, that will be able to process this, right? Because the key is linked to which reducer or which machine that is going to process this key value pairs. In this case, because the data set is reduced after your map task, so we can just use 1 machine to process it. And in this case, your reducer will have the logic to say, all right, 10, 61, and 46. I'll pick 61 as the largest and output this. And also this is not ideal, so this could be key value pairs. This should be key value pairs, right? Or you can write 161. Are we good? This is very simple, but also very confusing. Let's do it again. If you look at here, every machine, every map task takes a list of integers, right? And then they output 1 and the largest integer in that list. So why are we doing this? Why do we have 1 here? Anybody? Why do we have 1 as the key? Can we use 5? Can we use 0? Yeah, it's the dummy value again. You can use any number. But what's more important is all the map function use the same number. What does it mean then?
So you can make sure only 1 reducer can get the last list to reduce that.
Right, exactly. You are making sure that all these key value pairs are going to 1 place, right? So that 1 place, that 1 machine will have the largest integer from every map task and then combine them or generate the final result. But are we sure that 1 machine is enough? Well, in this case, it's enough because you're going to generate 1 key value pair for 1 map task, right? So you can expect that your reduced machine will not have too many, the input size to the reduced machine will not be too large. So you're okay. But there are different ways to write this, just for example. All right, so take this group by key, reduce, generate 60, 1 and 1, or 1 and 61, okay? All right, so here we want to generate a set of unique integers as the output. All right, so map task, again, it gets a chunk of the file of integers because we have a very large file of integers and then process it. So what would be your map task? Your map task will start to have some logic of unique integers, right? It will look at the values, the list of integers, and only find the unique ones and then produce it. Okay, so this logic of finding unique integers can be also in your reducer, but we are putting it in the map task to save communication time. So in this case, we are saying that, all right, I have an integer and I see it once. Oh, sorry, it occurred in my map, in the chunk, in my data chunk. It doesn't have to be once, can occur many times. Shuffling step will group all the values of the same integer and generate this. So the same integer might appear in multiple chunks, right? If you have 3, appear multiple times. In many map tasks, you have something like this, 1, 1, 1, 1, 1. And every integer key will only go to one reducer, so we are okay. In the reducer task, each reduce task is going to eliminate the duplicate again and generate integer as the output. So think about this. Oh, combine the output from multiple tasks, multiple reduce tasks, and you're done. But think about this. Our goal is to take a large file of integers and generate a unique integer, unique set of integer, right? So if we are going to do this in parallel, so these are data chunks, and these are my numbers, 1, 1, 2, 2, 3, 3, 4. Because we want to eliminate duplications, duplicated numbers, what are the 2 different types of duplications that we will have, given that this is running in parallel on 3 machines? Anybody? Well, I'll give you one example. The first type of duplication is you will have the same number in the same chunk, right? What will be the second type of duplication?
Amongst the different chunks.
Right, exactly. So you might have 2 appear only once here, but 2 also appear here, right? 3 here and 3 here. So in the MapReduce function we just introduced, who is in charge of eliminating within chunk duplications? Or your map task, right? Because your map task is going to read the entire chunk. It knows that, okay, you appear twice. We don't want you to show up twice. I only want you to show up once. So this will be my result. And who is, can your map task also eliminating between chunk duplications? No, it cannot, because it does not know about other chunks, right? Because if your map task here needs to know there are duplications in other chunks, it has to read this data chunk, and we don't want that. So each map chunk, each map task is in charge of eliminating duplications within chunk, and your reducer is going to collect all the result from all map tasks and reduce the duplications across chunks. Okay. All right, one more example, and we can take a break. All right, so now we're going to take a very large file of integers, produce the count of number of distinct integers as output. So the same as before, your map task will get a chunk of the file of integers and process it, and then do your reduce task. Let's look at a very interesting 2-stage MapReduce example. So far, we only look at MapReduce as one stage. You do map, you do reduce, you do map, you do shuffling, you do reduce, and you're done. But very often, we are doing map, shuffling, reduce, and another map, shuffling, and reduce. Sometimes it looks like it's redundant. You can just do it in one phase, but very often your data set will not be able to fit into your cluster, say 3 machines in one phase. So you have to do multiple phases. So let's look at here. You need 2 stages in this example, but you can also write it in one stage. So first phase, we want to eliminate duplicates in the large input file. So for map task 1, you will just produce integer 1 for unique integers. Okay, so you eliminate in chunk duplications. So something like this. Right, this is your chunk 1 key. This is the value in the chunk 1, and this is what you're going to produce. Right, you don't have 27 anymore. You eliminate the duplicates. The reduce task 1 will eliminate duplicates across chunks like what we did before, because this 7.1 and 7.1 will become this as the input to your reducer. So it knows that I'm going to reduce this and use a dummy value, say there's 1, 7, right? Or just 7, but usually you just have to do key value pairs. 8 and 1, you just output this. Great, so what's the output now? Well, the output now is a list of key value pairs where the key are the unique integers. So in your second phase, your map task 2 will get some unique numbers from the previous reducer phase as the input and output the key value pairs with key and count. So it will be something like this, and it will say 1 and 5. So what does it mean? This means 1 is a dummy value, 5 means in my list, I have 5 unique integers. So your first map reduce might output something like this. After it's stored to the distributed file system, you might have a really, really long list, say 2 terabyte. It's unlikely because the result has very simple data type, but let's just assume it's 2 terabyte, and one single machine cannot count how many integers we have in this large file. So we send it to multiple machines, still doing map reduce task, and ask the map task to count how many integers do we have here, how many integers do we have here, and how many integers do we have here, right? So that's this. The input is something like this. The output is 1 and 5, which means I have 5 integers in my list. And your reducer number 2, because you're going to use a dummy value as the key, and you know that each map task will generate 1 key value pair, so you can use only 1. You can use 1 reducer, which is fine. It will just sum up all the counts from the map task and provide an overall count, and you're done. All right, any questions before we take a break? Okay, so let's take a break for 10 minutes, come back at 7:01. If you have any questions in the meantime, leave it in the chat. I will answer them when I come back. All right, I'm back. Let's see. What do we have? Okay, questions. First question, can we assume reduce 1 can deduplicate old chunks? Yeah, based on the example we have, your reduce 1, your reducer number 1 should be able to deduplicate all chunks because it gets input from every chunk, every map task. Second question, how would you write the two-stage example into one stage? I was going to say that would be on your quiz, but let's do this. Okay, so if you look at here, this is two-stage example, right? So first stage, we are going to eliminate integers in we're going to eliminate integers, well, duplicates in a chunk. It'll be chunk number 2, not 1. Okay, number 2. And your reduced task 1 will eliminate duplicates again across chunks. But if your file is not that large, what you can do is in your map task, you will just output key 1 and what would be your value? Your value will be your unique integer, right? So in this case, you know that your map task is still eliminating duplicates within the chunk, and you're going to use one reduced task. And in this case, your one reduced task will say, okay, 7, 8. You might have multiple 7s because this is across chunks, duplicates. Then your reduced task will take this value list, eliminate duplicates, and count how many integers you have, then you are done, right? But the problem here is because this list can still be large, so that one reducer will not be able to do it, and you might need multiple reducers. All right, let's move on. All right, let's talk about combiners. So I show you a number of MapReduce examples, and how do we write more efficient code? Or how do we design map functions and reducer functions for it to run more efficiently? Just remember, every time when we say run it more efficiently in MapReduce, we generally are talking about reducing communication cost. So often a map task will produce many pairs of the form like this, key value pairs for the same key. For example, in our word counting example, if you have popular words like the word the, it could appear many times, right? So if every time your map task see the, it will produce this, that means you will produce many key value pairs of the and 1, even in the same map task, right? From the same file chunk. So instead of doing that, we can, in the map task, sum up the number of occurrence of the, and then we just produce key value pairs of the and n. N will be the occurrence of the in that file chunk. So in this case, we are going to, instead of sending many key value pairs, we are going to send only one key value pairs, and then we are done. So this means we can save network time, reduce the amount of data you need to transmit across the internet, across the network, by pre-aggregating values in the map task or in the mapper. So that's called a combiner. So combiner runs after the map task, before the reduced task. Combiner receives all the data from the map task as the input, and the output of the combiner is then sent to the shuffling and then to the reducer, right? Here it doesn't say shuffling. Using a combiner is optional, or you don't have to use it, but if you use it, it might save you time, but only if a combiner is suitable for the job. Because sometimes you might not be able to use a combiner, okay? So the instance of the combiners are run on every node that has run the map task. And this is why we're going to explain this in the second part of MapReduce. But this is important. Combiner runs after map task, and it's running on the node of the map task. The combiner is a mini reducer process. So it's very similar to a reducer function, but it's running on the map machine. So it might sound, I don't know. You might look at this and say, why are you telling me where I should run the combiner? But it will all make sense, I promise you, when we get to part 2. Okay, let's look at combiners. So if a reduce function is both commutative and associative, we can then use a combiner. If you're not familiar with these terms, let's look at this example. So commutative means A plus B equals to B plus A, right? So that means you can pre-aggregate your data. Associative means you can add 2 values first, then add the third value, or you can add the second and third value, then add the first value, and it will be the same. So in this case, this example, this is a file that we are going to produce a summation of all the values, right? So you can have a combiner after the map task, pre-aggregate the values here, then send it to the reducer. Or if you don't use the combiner, you can just send the raw value to the reducer, ask the reducer to do the summation. Okay, so the first scenario with the combiner means you have less key value pairs that you need to send across the network, and you will save time. If a reduce function is both commutative and associative, then you can use the combiner. So sum is a very good example. But if the reducer cannot be used directly as a combiner because of these 2 properties are violated, you can still do something to use a combiner. So for example, average. It says write a third class, but let's look at what does it mean. So if we want to calculate average, in this case, you cannot just sum them up, right? You want to know the count, the number of integers or numbers you have in this chunk. So instead of producing a key value pairs where value is the sum, you produce a key value pair where value contains more knowledge about this chunk. It has the count of the numbers in this chunk and their summation, right? So very often people did not write the key here, but remember it always key value pairs. And in your reducer, now to calculate average, you just take all the sum, divide it by all the count, and you're done, right? So this way you still save network time by adding additional information, which is the count here. So let's look at another example. We want to write a MapReduce program, take a very large file of integer, produce the average of integers as the output. Map task, produce key, number of integers, and sum of the integers for each chunk as the output. Your key could be the same value for all mappers like we did before. It would be a dummy value like 1. That means you will only use 1 machine to run the reduce task. The value is the number and sum tuple, right? Number of integers and sum of the integers. In your reduce task, you have 1 single reducer, sum up all the sums of integers from all the map tasks, sum the number of integers, calculate the average, and produce something like this. So look at here, we have a 1. What is this 1? Well, again, it's a dummy value. So you can do 1 and average. Doesn't really matter. Okay, so don't be confused though. Why are we using one as a value here? All right, so since every map task will be able to summarize a large chunk, so single reducer might work. Let's say you have 1,000 map tasks. How many key value pairs you would have for your reducer? Anybody? You only have one reducer, right? Okay, great. This is a tricky question. Yes, you only have one key value pairs, not 1,000. You have one key value pairs. The key will be 1. What will be the value? The value will be a list. How many numbers do you have in that list? 1,000. Great. All right. Thank you, everybody, for answering. Let's look at one example. Now we want to calculate how many big words, medium words, small words, and tiny words in this text. And you have a really large text. So big ones are the yellow ones, medium red, small blue, tiny pink. What would be your map and reduce task? Look at the chunks. You have 2 chunks. This means you are going to have how many machines to handle this map reduce job? Well, usually you just have 2, right? Because machine 1 will handle this chunk, machine 2 will handle this chunk. When we start to say it's a chunk, which means it will be stored on one machine. So if it's on one machine, you just have one machine to process it. So your map task will read all these words and generate key value pairs like this. So are we using a reduce? Are we using a combiner here? We actually do. We are using a combiner. If we don't use a combiner, what would be your key value output? Right, you have yellow 1, yellow 1, yellow 1, and 17 times, right? You have 17 yellow 1 key value pairs. So we're using a combiner, we combine them, and that is great. And how many reduce functions do we have? Sorry, how many reducers do we have? In this case, these are going to send to the shuffling step, and all the yellows will go to the same reducer, all the red is going to the same reducer, blue is going to the same reducer, pink is going to the same reducer, right? So we have 4. But this is conceptually, you have 4. This 4 reducer can actually run on the same machine. It's not like the map task. I will explain why. Okay. All right, so map task, shuffle, reduce task. Right, so now you have yellow, 7 and 20 becomes 7, 20 to the reduce task, yellow. And the reduce task, we just add 7 and 20 and you have 37, then you're done. All right, so in summary, in MapReduce, the input is key value pair and output is also key value pairs. Your map code is written by the user, like what we have been doing today. The map task will process chunks, produce sequence of key value pairs. But this is not really the key in usual sense. The key doesn't have to be unique, does not have to be unique. Then the group by key or shuffling step is handled by your environment, can be Spark. Collect all the key value pairs. Value associated with each keys will become a list of values or key value pairs with the same key go into the same reduce task, and you will need to write the reduce function, produce some output, still in the key value pair format. All right, that's the first part of your map reduce. Any questions?
Hi, Professor. I have a question about the combiner.
Sure.
So actually, when we are dealing with each word, are we creating every key value pair on every word? For example, the word the, and then we create a pair which the key is the and the value is 1. And the combiner helps to combine all those same pairs.
Yeah. So
Okay.
that's the algorithm you have to write.
All right, thank you.
You're welcome. Let's see. Oh, so there's a question: what's the relationship between reduce task and reducer? That's tricky. A reducer is usually a machine that processes reduced tasks, but reducer can be also a program running on a machine that processes reduced task. So it might be clear after we finish the second part of the map reduce. So let me know if you still have questions once we finish the second part. Okay, map reduce second part. I really like this diagram. If you don't remember anything, you have to remember this.
You're not sharing it, Professor.
Okay, great. Thank you. Here we go. So look at this diagram. You have a large file. And what are all these rectangles? Anybody?
Chunks.
Right, these are chunks, right? These are data chunks. And this implies the entire chunk is what? Stored on one machine, right? These two chunks might be on the same machine, we don't know. But what we know for sure is one chunk is on one machine. And what are these M's? Well, this is your map process or your map task. You can think of this as a program running on some machine. And for sure, based on our what we have discussed so far, we say you have to bring your computation close to your data set. This M should be on the same, running on the same machine of this data set. Okay, are we good? So if we are good, now this is the input for your map task. This is the process for your map task. The output will be your key value pairs. And we call this intermediate result because this intermediate result is still stored on this machine, the machine with your map task. So if I draw this, this is one machine, this is another machine, this is the third machine. Okay. And you will start to see why this is important. And then group by key, once your map task has finished, it will notify the primary node, and the primary node will take a note, say, all right, map task number 1 has finished, and let's do some shuffling. Once it does some shuffling, it might generate something like this. Oh, it will also wait for other map tasks to finish and just do the shuffling, generate something like this, and tell the reducers or the nodes, the computer nodes that are running the reduce functions, say, find all this data and do your reduce function and generate some output. Okay. But it's very important to think about how data is stored and transmitted over the network because that's high cost. So starting from here, we know that this big document is stored where? Where do you store the big document? Anybody? Well, it's on a disk, yes, but where? On an on the machine, well, okay. On the local file system or on a distributed file system? HDFS, yes, thank you. So this is stored in the HDFS so that we have multiple chunks on each machine. And once this map task finish processing, where do we store this? So it's important to know that this is intermediate result. So it's not stored back to the distributed file system because that will take time and high network cost to slice the data into multiple chunks and replicate the data. We don't really need that for the intermediate result. So this will be stored on a local machine. Okay, so that means it was stored on this machine. And after we group them, this group by key function is running on the primary node. So it has this information. It has to tell the reducer where to find it, right? So how does the reducer get the data? Does the reducer get the data? Well, does the map task send the data to the primary node, to the reducer, or the reducer gets the data directly from the primary node, from the map task? 1 or 2? Anybody? Well, to think about this, the easiest way to save computational cost is don't send your data twice, right? So your Spark or your MapReduce implementation actually just tell your reducer, say, all right, go to map machine number 1 and go to this address. You will be able to find this key value pairs that you need. So your primary node only tells the reducer the address of the output from the map function, and your reducer will directly get the intermediate result and process them and save it to an output. So where do we save? Where do we store the output? Well, the output is again saved back to the distributed file system, right? Now it's not intermediate file anymore, and we might need the output for other stuff. So it's important to keep the data in multiple places. So there's a question, can any of the computer nodes doing the map task then be used as a reducer after they finish their map task? Yes. So it's funny that you can run Spark on your own laptop. You only have one machine, so that means you're running map task and reduce task on the same machine. But many of the computers right now are multi-threaded, or you can have multiple CPUs. So that sometimes makes sense. So one machine, one node can run multiple tasks, and it can run both map and reduce tasks. All right, so who is going to decide how do we run this? So there's a question, how does the primary node process the intermediate file without transferring the files? It does not really aggregate all the values. It will just get the key and tells the reducer to find the keys from the intermediate file. So the question is, can you repeat the 1-2 route again? Okay, so here. So route number 1, after a map task finish the result, send to the primary node. So I just assume this is the primary node. Send the result to the primary node, and the primary node will just aggregate them like we did before, generate something like this and send to the reducer, right? That's route number 1. Route number 2 is once it's done, the primary node will know it's finished and collect all the keys from every machine and send the address of the file to the reducer, and the reducer will just get the data directly from the intermediate file. So it's route number 2, not number 1. Key value pairs never been sent to the primary node. It's always directly between map and reducer. All right, so running this in parallel, you can see map task 1, 2, 3, reduce tasks. And this is your distributed file system, distributed file system. This is your intermediate result. So this is a local file system for this computer. And this is a partition function. This is what we were talking about, the shuffling, right? So after the shuffling, we know that which node, which reduce task needs to process the result. So once we do the shuffling, the reducer knows how to get the data or where to get the data and have data like this, doing the reduce task, save it back to the distributed file system. So in this example, typically in your MapReduce environment, your MapReduce environment will take care of partitioning the input data, right? That's the HDFS, scheduling the program's execution across a set of nodes, which map tasks should run on which node. Performing the group by key step, there's usually a hash function by default assigning key to reducers. Handling machine failures, if for some reason some machine died, let's say this one died, your primary node will know and reassign the map tasks to other machines, right? Because this is a distributed file system, so the same chunk should be stored somewhere else, and your primary node will know because it has the global address book. Managing required inter-machine communication, for example, your reducer or your map task might needs to talk to each other about sending data or different between map tasks. They might need to talk to each other. Your primary node will coordinate the communication. So data flow. So what we have been talking about is actually going to become important here. The data flow is important. So the input and the final output are stored on a distributed file system, like we said, we talked about in the previous slides. Your scheduler, your primary node that is going to schedule the task, will schedule map tasks close to the physical storage location of the input data. That means it will always schedule the map task on the same machine of the data if possible. If it's not possible, maybe other machines of other available machines on the same rack, right? That will be close. Intermediate results are stored on local file system of the map workers, and the output is often into another map reduce task. Okay, like what we seen before this two-stage map reduce task. So the coordination, your primary node will take care of the coordinations. It will know the task status. It could be idle, in progress, or completed. So idle tasks will be scheduled if you have more workers become available. Your primary node will know how many workers are available. When the map task is complete, it will send the primary node the location and the size of its intermediate files, one for each reducers. If you have R number of reducers, it will generate R files, because remember that partition function is running on the map task. Your primary node pings your workers periodically to detect failures. So if one worker does not reply for a longer period of time, we know that you might lose that worker and you need to reschedule that task. So why do we care about data flow? Well, failures. If your map worker failed, the completed map tasks or the in progress map tasks are going to be reset to idle. That means it has to be rescheduled to other machines to run it again. So idle tasks eventually got rescheduled on other workers. for your reduced worker, if your reduced worker has failure, only the in progress tasks are reset to idle, and you're going to restart this reduced task on other workers. If your primary node has failure, then all your map reduced task is abort, notify the client to see if you want to restart it. All right, so look at these two failures. This one we know, right? This one is really, really bad because the node that's coordinating all the tasks has failure, so you have to rerun everything in most of the cases. But what's the difference between these two? If you have a reduced worker failure, you only restart the in progress one. Map task failure, you have to restart this too. Why? Anybody? So, all right, we have an answer. When map workers fail, all intermediate files are lost. Why is that? All right, awesome. You guys got the answer. Because all the map results are stored locally on the map node. It's never on the DFS, right? So if a map worker died, we lost all the files, even if it's completed. Okay, so your reducer, the completed output will be sent back to the distributed file system, is replicated. So if you have a reducer worker failure, you're okay. Just restart the in progress tasks. Okay, so this is important. This is very, very important. If you, well, the takeaway here is you want to understand how data flow in the MapReduce environment. So when you write your code, because you are going to expect there will be failures, right? So you want to better prevent data loss and write your code more efficiently. All right, how many map tasks and reduce tasks? Usually you have much larger map tasks than the number of nodes in the cluster. That means one machine can run multiple map tasks. 1 DF chunk per map task is common because you want a task to access the chunk for any process. Improve the dynamic load balancing, can speed up the recovery if you have worker failure. And usually your R is much smaller than M. You have less reducers, less number of reducers than your M, and your output is spread across R files. So why do we usually have smaller number of R's than M's?
Because of the reshuffling.
Well, no, it's usually because your M is your map tasks are handling much larger file, right? It's handling the raw data. And based on the logic in your map task, it can do filtering, it can already do some computation, or even a combiner. Eventually, your reducer will not need to handle such large data. So we only have much smaller reducer tasks for M. So Google example, 200,000 map tasks, 5,000 reduced tasks on 2,000 machines. And we look at combiners. So remember we say your combiner will combine all the values on a single machine. That means where do we run the combiner? Are we running the combiner on the map node or on the reduce node? Map node, great. So that means your combiner also gets data from the intermediate file system, from the intermediate file on the local file system, and it will store its result in the intermediate as intermediate files in the local file system, right? So this way, much less data needs to be copied and shuffled. Works if reduce function is commutative and associative. Also, there is one thing that we can do about partition. So partition is a way to control how your data can be would be processed by the reducer. So very often, well, we don't really do this. I think in our homework there is one assignment asks you to overwrite the partition function, but your Spark, your MapReduce implementation has a default one. So it will control how your keys are partitioned, reduce the needs to ensure the records with some intermediate keys end up, at the same worker, because you might have that requirement. Here, system will use a default partition function. It will be something like this. And hash function, input is your key. And the hash function can take the input and generate, let's say, an integer, a unique integer. And if you mod this by R number of reducers you have, it will give you one number, right? So let's say your R is 100. This will give you a number from 0 to 99. Then you know which reducer you are going for. And if you have the same key, you are always going to the same reducer. But sometimes we want to overwrite this hash function. For example, we might want to use something like this. If URL is the key, we just use hostname and URL, send it to the hash function because we want the URLs from the same host to end up in the same output file, although we still want to use URL as the key. So there's a question why we mod R instead of M, because shuffling is the step of order all the key value pairs from the map tasks and assign them to reducers, right? So that's why you want to mod R, because you want to know which reducer you want to assign to. So implementations of MapReduce, you have Google's MapReduce. If you guys eventually go work for Google, come back and tell me. But there's Hadoop that you can try, and also Spark. So let's look at more examples of MapReduce. This one is very simple. We want to do relational join. You have two tables, employee and department. We want to be able to do this, right? Join is very easy in a relational database, but if your data is large, relational database might not be ideal. So what we can do is, this is the desired output. We can write MapReduce to do the join. In your map task, write out the key you want to do join, write out the value, says here is the data content from my table, and my table name is called employee, okay? And when process the second table, you say, here's the key I want to use for join. Oh, sorry, the same table. If you're processing the department table, here's the key I want to use for join, right here. And this is the value. This is my table name. This is the data content. Right, very easy. In your in your reducer, all key value pairs with the same key will go to the same reducer. Your reducer will look at values like this and will know, right, this value is from the employee table. This value is from the department table. Let's merge it and generate one value like this. And also you can eliminate this as well. You don't need duplicate values, but this is very simple. You can do joins. We also have distributed sort, but I'm going to skip this because I think you'll be able to learn this by yourself. I am going to do matrix multiplication. All right, this is very, very, very important, matrix multiplication for MapReduce for many reasons. Matrix multiplication is very commonly used in computer science. Well, especially now you do deep learning and all that. And this is a very basic operation, but it's very time consuming. Assuming we have two metrics, A and B, A times B equal to C. This is to tell you how to do matrix multiplication. I'm sure everybody knows how to do this, but I still want to tell you, if you want to multiply A and B to get C, A is of dimension 2 by 3, B is dimension 3 by 2, and C will be dimension 2 by 2. How do we get the value 11? Anybody? (11) is at the location 1, 1, right? Row number 1, column number 1. That means we have to take row number 1 from A and do a dot product with the column number 1 of matrix B. What is the dot product, you asked? Okay, it's 1 times 1, 3 times 0, and 2 times 5 equal 11. So, great. What did you see here? When you calculate 11, you only need this and this, right? When you calculate this 10, what do you need? Which row and column do you need from A and B? Anybody? Okay, great. This is an answer. So when you calculate 10, you only have to use row 1 and column 2, and we know every component here in C can be calculated independently. So that means we can do parallel processing, right? You can have 4 computers, each of them process 1 component, and you are done. So let's look at how we write a MemReduce code. I assume you all know how to do matrix multiplication yesterday or today by just next slide. Let's look at how to do MapReduce on the matrix multiplication. Your map tasks for each element in A here. We produce something like this. Let's look at it. A11. A11 is here. We produce a key value pair, says my location is 1, 1, my value is 1. Oh, sorry, this is not saying my location. This is saying I am going to location 1, 1, and my value is 1. Then it says I'm going to location 1, 2, and my value is 1. So why do we only have 1, 1 and 1, 2 here? What does it mean then? If you look at C and look at this component, which component in the matrix C require this 1? Well, when you calculate 11, do you need 1? Okay, yes, you do, right? When you calculate 10, do you need 1? Yes, you do. So that means A11 needs to be sent to 2 locations for dot product, right? So that's why you have 1, 1 and 1, 2. So this key is actually indicating the location in the C matrix. Now you know how to do 1, 2, right? You send to the location that needs you. So who needs 1, 2? Who is 1, 2? 1, 2 is 3. The location in C that needs 1, 2 would be 1, 1 again and 1, 2, right? So 1, 1 is this. It will need this and this. 1, 2 is this. It needs this and this. Great. So now we know how to send all the elements in A. For B, let's look at B. B11. Which location should we send B11 to? Well, again, all the locations in C that require B11, right? So that would be 11. And what else? Who will need this one?
9.
Number 9. Great, thank you. So 9 will need this and this, right? So one has to be, B11 has to be sent to this location, 2, 1. as well. Awesome. So this is how you do matrix multiplication in MapReduce for your map tasks. But more generally, you have to send out more information. You have to send out information like, this is the location that you need to go, right? This is the location in C. This is saying that, oh, on the last slides, we only have these two things. The location in C and the value is the value in the matrix A or B. But in general, when you start to write the program, you know that your reducer will not be happy if you only send this, because you need more information to tell me that, okay, are you from matrix A or B, right? Which location are you coming from? So you need to send out A, I, and J. But because we already know that this is from IK, so we can actually eliminate I, because everyone will share the same I, so we just send out this. If you don't understand this, just write it down on paper. You have to be able to do that for, yes, need the index, like someone said in the chat, Jin Chen. You have to practice this on paper, because this will be on our quiz next week. So the same thing happened for B. You do the same, indicate that you are going to this location. You are from B. This is your index. This is your value. All right, so that's it for today. We are out of time. Next week, I'm going to cover some more of this, just a recap. But two things that will be on your quiz next week is you need to know how to do MapReduce for matrix multiplication in one phase. And also, you need to know how to do MapReduce in two phases. Here. So the reason why we need to do two phases is because sometimes the matrix is just too big. You will not be able to handle them in one phase. So, all right. So today I have office hours. If you want to talk to me, you can stay. If you are not, you can leave. Thank you, everybody. Have a good night. I will see you on Monday. Make sure you read the textbook. On Monday, we are going to release your assignment 1. Make sure you start early, work on your quiz. Sorry, chapter 2 as well. Yes, thank you.